So exercise 200, page 497. I'm going to just have a look at question number 10, and then for the BTEC course, question number 11 is a required question. But this is a way of finding the area underneath the curve using a numerical method. So if I were to plot this function, or these data points rather in this question, I'd get this graph underneath here with these points on. If I knew the value of the function, the curve that went through these points, I could integrate that function between the limits 0 and 8. But without the function, I need to fall back on a numerical method to find the area of the curve. And Simpson's rule is one good way to do it. So, in other words, this particular idea is a numerical way to estimate this integral between two limits a and b. It's given approximately by, so that's what this symbol here means, approximately by 1/3 of w, where w is the width of an interval, times the first ordinate plus the last ordinate. So what do I mean by the first and last? Well, these are the ordinates here. So first ordinate is the y value for that first point. And then when x equals 1, the second order, well, this will be this value here. The third ordinate would be that value there. The fourth ordinate would be this value on the y-axis, and so on. So that would be the fifth ordinate, and so on, up to the last ordinate here. So this would be the last ordinate. So the first ordinate will be this one, 0 in this case. The last ordinate would be this value here. And then we've got the other ordinates in between. So this would be the first value of x, second, third, fourth, and so on, fifth, sixth, seventh, eighth, and last in this case. For Simpson's rule to work, you must divide it up into an even number of strips. So 1, 2, 3, 4, 5, 6, 7, 8 strips, so an even number of strips, which gives you an odd number of ordinates. This must be an odd number down here, this last one. So once you've done that, you've divided it up into 8 equal strips by dividing the whole interval. So between 0 and 8, divide that by 8 and I get 1. So each interval is 1 apart. 4, 5, 6, 7, 8, which gives you your first through to your last. So these effectively are the ordinates. Here, the y values. So first ordinate, second, third, fourth, fifth, sixth, seventh, eighth, and ninth, or ordinate, or last ordinate. So these are the ordinates. So you don't need to plot it for this particular question, but I have plotted it so you can see those values on the graph and the strips it's been divided up into. So now we need to devise a table so that we can work out the value for the area underneath this curve using Simpson's rule. Don't actually need a table here for this particular question, the area. So we just plug the numbers in. It's a third times the width, which in this case is just 1, the width of each interval, plus then this will be the first, this will be the last from the table, plus 4 times the evens, which are the second, the fourth, the sixth, and the eighth ordinates, plus 2 times the odds, and the odds doesn't include the first and the last, and that will just be the third, the fifth, and the seventh. So now it's just a case of adding up these ordinates in these brackets and then working out the solution to get the area of the curve. Going back to autograph, I could extend this question by trying to use autograph. So let's have a look at these data points to try and fit a curve to these points and then use that function to integrate it between the limits to come up with an estimate for the area. So if we look at these data points, it looks as though it's not a straight line. They are curving up, apart from this last point here. So it may be that this is a part of some sort of square thing. So I could put in y equals ax squared. Okay. And you can see this is curving up. The steepness of the curve depends on the value for a. And we've got a constant controller here, which allows us to change the value of a. So if I make a smaller, we can see I can change the step size to smaller or bigger amounts. If I change the step size in fairly small chunks, you can see that the curve sort of approaches these data points. It's not a very good match, but I could say that this function looks a little bit like y equals 0.16 x squared. So I could take that function and integrate it between the limits. So from this particular function we could say y equals 0.16 x squared. So the area equals the integral between 0 and 8, because those are our limits, of 0.16 x squared with respect to x. And this would equal 0.16 times x cubed over 3 between the limits of 0 and 8. So I can now put x equals 8. Obviously when x equals 0 the whole thing's 0. So it turns out the area equals 0.16 times 8 cubed over 3. And we could work out what that was and see how close that was to the answer that we had from Simpson's rule.